Hello everyone, welcome back. Let's slowly start with this session where we're gonna show a little bit more about the capabilities of VMD in terms of first creating nice figures, and I'm gonna show how to create movies in a relatively simple way. I mean, simple movies, let's start with that. And then we're gonna switch to the force field toolkit tutorial. Gonna go over that in this session. Okay, I will wait a couple more minutes. Before starting, see if someone else is coming to join us. Okay, let's start. So if you remember the first session in the morning that I gave, we were discussing how to make the most from VMD. And one of the things that I mentioned was that this super important feature of VMD, which is save your visualization state, your VMD state. And that VMD state is basically anything that is loaded into VMD. Like for example, here I have two molecules loaded with a trajectory also for the second one up to 2400 frames. All my representations that I carefully created for this molecule, for example, everything is gonna be saved, okay? So next time when I open this again, I can just load this and it's gonna appear automatically. So another thing that is important to mention is that there is this concept in VMD about what is called a viewpoint, okay? And basically a viewpoint refers to anything that you see in the display and anything that is necessary to reproduce that display, that view, okay? So for example, I listed here a few things that were how can I switch between slides? Shift Control down. Doesn't work. So I mentioned that the viewpoint incorporates not only the position of the camera, the viewing angle, but also any representations that are on in that view, in that display, and any selections that I use, everything that entails the representation. Okay. So therefore, one good use of a viewpoint, if you think about it, is, okay, let's say I have my system. Let's use the other system for now. So let's say I have this protein system that I mentioned. Let me switch to the normal random mode. Okay. And I'm interested in studying the interaction of a drug, of a ligand with the protein, so I can zoom in into the system, or in this case, I move onto the system. Let me hide the lipids. That's faster. Okay. Okay. So I'm interested here in around this heme here. Okay. And the drug is basically this residue, this compound here. So I want to look at this. Okay. And then I want to look at something else. Like, for example, what are the lipids that interact with the protein? Okay, I want to look at the different position, different camera angle, different anything in my system. Okay, so that's how I can make use of one of the tools in VMD, what is called view change render, to basically record and save all these viewpoints. Okay. And therefore, I can come back and switch them back and forth between the viewpoints. Okay, I don't need to again navigate through VMD's scene and try to find the position of the camera. So let's do that. Let's use this is view change render. So I already have some viewpoints saved here. This is a list of viewpoints. So I'm fine with this viewpoint. I like it. So I have a clear view of the heme group with the drug here. So let's do that. Let's save this here. So once I'm here, I can click Save Viewpoint, and now I have a third viewpoint because I already have the other two. And now let's do another viewpoint for this molecule. As I said, let's go back and now I'm interested in, for example, the interaction of the protein with the lipids, okay, with the membrane. So I'm interested here in the bottom. So, and for that, I need to show the lipids, but I want to show the lipids in a different material. So let's do like something like transparent or something like, okay. All right, so I'm looking here at this point, at this position. Let me switch. Okay, I like this better. Okay, so I'm interested here. So now I go here and I save my new viewpoint that is a different part of my system and click Save Viewpoint. So now if I go back and forth between these two, I can retrieve viewpoint number 3, which was the heme group. And I go here and I'm back to this view. and see that now I don't have the lipids anymore, because the lipids were the representation. This representation that was the lipids was not on when I save my viewpoint. Okay, and let's go back to the other to the last viewpoint that I saved, which was the lipids. So now I can go retrieve, and now the representation that was the lipids that I just modified now is on. Okay, so basically I can save as many viewpoints as I want, and that's handy, because if you are analyzing your system and you want to look at different parts of the system, and you want to remember what you look, or you just go back, you want to go back to that and show a collaborator, for example, oh, look at this and now look at that. It saves you a lot of time. But what I wanted to say is that not only save you time when you are exploring your system, okay, I like this part, I can save this viewpoint and then come back to it, but also it helps, ViewChain Render helps you generate kind of like a user-defined movie script, okay? By ways of allowing to create in the second menu here, a movie that basically is a collection of viewpoints, one after the other, and it generates a transition that if your viewpoints are in different positions, the camera at different positions in the scene, it's gonna interpolate the two geometries and create basically like a path between the two, okay? So let me give you an example with the other system that I have here, which is a simpler one, and I think it's a little bit easier to understand. So let me reset view. So now I have this is a carbon nanotube, which is basically like a tube made of carbon atoms, where you flip or you grab a graphene sheet and you just roll it in different dimensions and you get like a tube, okay? So these nanotubes are very important in material science because they have been hypothesized to be very effective materials for electron transport or other electronic properties, because as you may know, the graphene sheets are very good conducting electricity. They have this pi stacking of electrons. Another usage of these nanotubes is that given that they can roll, these sheets can roll into tubes of different dimensions. The mouth of this tube is flexible. They can act as channels, basically artificial channels. So where you have like a perfect tube where you can where a substrate can go through, and depending on the size of the tube or the mouth, different substrates can go through. Okay, it's kind of like a filter channel at the same time. And even more interestingly, when the tube is small enough, the diameter is small enough, water can solvate this tube in a particular arrangement of water molecules, which form a single file of water molecules, like kind of like a wire of water molecules. And you can see it here. This is actually a simulation that I did where I was interested in studying proton transport, meaning in the proton in a water system, you add an extra proton and see where it goes. Okay, and you may be familiar about the proton transport in bulk water, which is due to a mechanism that basically there is no single proton that is moving through the water, but each water molecule acts as a hop, a space where the protons can hop between different waters, and therefore the propagation of this extra proton is much faster compared to what would be a single atom or ion just going through the thing. So, but let's go back to the visualization. So here I have a part of my system where I have the nanotube and the single file of water molecules here. So and what I try to do here is to convey the message of this proton transport is I want to explore this from different points. So what I did is I saved a few viewpoints for this system. And since I have a trajectory, I can save the frame that I selected in VMD can be part of my viewpoint. So if I select the frame 0 and I save my viewpoint, then the next time I retrieve this viewpoint is gonna be at frame 0, okay? So I have two viewpoints, viewpoint 1 and 2 here, where the first viewpoint is kind of like in the center, inside the tube, looking through the tube, and I'm here at frame 0, okay? The second viewpoint, if I click retrieve, it's gonna show me that I'm at the end of the tube, okay? Like I went through the tube, and I'm now at the last frame 2399, okay? I had, so the last frame, and I save that at the last frame. So with those two viewpoints, if now I use these two viewpoints in this, and in Viewpoints to create a movie, when it's gonna happen, I can show you the preview here. So let's go back to viewpoint number 1. So if I show you the preview, I click preview. And what you're seeing here is basically a geometric interpolation between the initial viewpoint position and the final viewpoint position in time, because I have different frames in my trajectory, okay? So what is happening here is this is kind of like how the script of my movie is gonna look like. I'm going to go from one point at the beginning of the tube, at the beginning of the trajectory, to the end of the tube at the end of the trajectory. Does it make sense? And this is a very simple case that shows how setting up two viewpoints and loading them into Viewpoints render can quickly generate the script. When I'm talking about the script, I'm not talking about like the coding script, but like the actual plot of the movie, like what is happening in the movie, right? Okay, so let's abort the preview. Let me show you how it's done. So I can clear the list, and I just select viewpoint number 1, and I click add viewpoint to the movie. Then I select viewpoint number 2 and put add viewpoint to the movie. And now it's giving me a transition time, automatic transition time, that is kind of like estimated from the time it takes to go from frame 0 to the last frame. But I can change that. I can make it quicker. So maybe this was fine. I like it, but it was too slow. So I can change the transition time. Let's say I can do it like in 30 seconds, which is much, much faster. So now if I do preview of the movie, it's gonna be much faster. Okay, it's gonna go over the frames much faster. So that is, okay. So the last thing that I wanted to say is that now that I have this kind of like sequence of viewpoints to create a movie, I can connect this to Movie Maker, which is a plugin for the creation of movies. So let's go to extension, visualization, and Movie Maker. So if I enable here the Viewpoints render, I can now create a movie with the Movie Maker. And what is a movie? Let's spend 2 or 3 minutes talking about what is a movie. A movie is just a collection of frames, right, of still images. So what is going to happen is VMD movie generator is going to render a frame of what I'm seeing at the beginning, then it's gonna move my system to the second, to the, in time here in the trajectory. It's gonna move the camera, and then it's gonna take another frame, another render, and so on and so forth. So basically what a movie generator is gonna generate is a collection of images or render files that then I can post-process into a movie, okay? So let me show you a few more things here. So I can select here a movie generator, the renderer that I want to use. Remember that I showed you earlier that different renders use different accelerators. Like for example, the tachyon optics uses GPU acceleration. There is an internal tachyon that uses CPU. So basically, if I want to render a nice figure, I can use the tachyon optics. And what it's gonna do is, again, it's gonna load all the information for my viewing angle, everything. It's gonna render a frame. That image is gonna be saved, and then it's gonna move in time and in space, and it's gonna render again, and it's gonna do that automatically, okay? So I can also, so to use this recipe that I created for the viewpoints, I need to go to user defined here. And then I can select the format of the movie. I can even create a GIF. I can create with different formats, depending on the platform that you're running, whether it is Windows, Linux, or Mac, you will need some additional programs to complement this. But in principle, you can go here and deselect the delete image files. So basically, once it finishes with all the rendering, you will get all the files here in the directory that you select. Sorry, I had to mute. Okay, so are there any questions so far? Okay, let me show you how it looks, this system, using the new real-time ray tracer render mode. So let's go to display, render mode, and use the Tachyon RTX. Let me make it a little bit bigger. So now I'm using, you see here, I'm using again this reflective materials that have, since the system is relatively simple, I'm using more powerful visualization tools and options to make it pop up more. And let me show you how it looks if I change the material that I recently did. So this is for the nanotube. These are only 3 representations, and this the nanotube here is in this material called AOAG. Okay. So let me show you. Let me check one thing. Yeah. So let me show you what happens when I change this to RT Chrome, which is a different material that has more reflective properties. Okay. So now it looks quite different, right? It looks like kind of like a glass bubbles, glass structure reflecting all these things. And this is live on the VMD. So I can move the molecule. I can deselect some representations if I want to. Let's say I want to change. I want to hide the waters. I can do that. And I want to change the color of the water. For example, instead of using the default color, I can use I don't know, yellow to get more contrast. Okay. Okay. Any questions so far? All right. Let me show you one more thing that I think it's interesting. And for that, I need to reload VMD. So let's do that. Where was I? Okay, so John mentioned that you can also I have the same system here. VMD is able to now show stereoscopic images and render in such a way that you are able to generate virtual reality compatible scenes and movies. Okay, so let me show you an example of how to do that very quickly, and then I'm gonna show you the result that I did in the video that I posted in YouTube. So this is the same system, okay? And let me go back to the view change render. And something that I didn't mention is that once you create all these viewpoints, you can save these viewpoints in a file. Therefore, the next time you need to load this file to create this, to recover this. So I have already saved this file, and this is this test.bpt file. So when I do that, I have these two viewpoints that I already mentioned, that I already show, okay? This one here. Okay, let me show one more thing. So this is a display. I don't need this, and I need this. Okay, so you can go to our website and search for VMD VR movies. And when you have here is this short tutorial on how to create these VR compatible movies, okay? And what it is basically is the idea that you're gonna render first, you're gonna render things in a stereoscopic view, and I'm gonna show you now how. And that means if you've seen these cameras that are basically like a spherical glasses that record everything that is happening around you. So therefore, when you process that, you will be able to turn around and look what's behind you, right? So that's what we're going now. We're gonna render, but now instead of only capturing what is in front of me, I'm gonna capture everything that is around me so that I have the option to move around after I created the movie, okay? I not only look at what is in front of me, I can look also at what is around me. So let's do that. So here we can see that the main things that you need to change are a few environment variables of VMD. And actually this is done in the TK console. So let's do that. I need to change this variable to 1. I need to change the second. There are 4 variables. I'm just following what is here. And see if it works. And this one is the most important one that says, let's render with using, when you use the render optics, let's render in stereo. Okay, so now let's go to the render that was the tachyon optics here. Let's use the interactive, which is the GPU accelerated, and let's click start render. I think I'm missing a file. Let me check 1 second. Oh, okay. I wrote the. This is what I need. Where's the code? All right. Let's try again. Okay. So now let me open this a little bit and let me try to explain what is happening here. So first, if you know a little bit about virtual reality, you can imagine that in order to get some perspective, you need to have different, your different eyes have to have different views, right? You have to have the left eye has to be a little bit different than the right eye. So basically what we are showing here is that we have actually rendering 2 different eyes. The top one is, for example, the left one, and the right one is the bottom. And not only that, but we are also rendering everything that is in front and also behind. Remember? Did I tell you that? So if you look, it's kind of like interesting. Let me show you a different scene. For example, where we are like, let me use the camera navigator again that I closed. Okay, let's see. I'm a little bit inside now. So let's render again. You see, now I have things in front of me because I was looking through the tube and I see the things that are in front, but I also see the things that are behind, right? So I'm sitting here and here I see the things that are in front of me, and here I see the things that are behind, okay? And I can kind of like look around and rotate, and it's gonna be a little bit spooky, but it's nice. So what happens? If I set up these variables so that it renders in this stereoscopic way, what's gonna happen is that if I run my movie maker and create all these frames, the final result is gonna be something like this. Let me show you. So here I have my YouTube page. Let me, yeah, okay. So this is the video that I generated, which is basically the same trajectory that you saw, the same files, everything is the same. But now in YouTube, I can click and drag using my mouse to see things that are around me, okay? So that's the key. So now I see if it, okay. So now I can click and drag, for example, and look at things that are around me, okay? I can see this proton is hopping between these 2 water molecules, okay? I can see in the back, they open the first part. I can turn around. I can focus on this carbon atom and the reflection. Okay. And you can imagine that this video, if you have a VR headset, you will be able to look at it and do the same thing, but the images will look much better. Okay, it's gonna be much better, more crisper. The movement, everything's gonna be better. So again, if you're interested and if you have I know this is kind of like it's not very scientific because it's more of a educational tool. Maybe if you wanna show it for we have a lot of experience showing this to young students like high school and younger, and you can actually see, if you use this in a VR headset, you can really see and interact sometimes with the system. Okay, any questions? I'm gonna copy this. I think I can share. Yeah, I can share this in the chat. See if I can get this chat. Let's zoom. Chat. Okay, so you can explore, you can play around with that as well. Okay, any questions? No? Okay, so let's switch gears and let's talk a little bit about the second talk that I gave that is related to the parameterization of small molecules to get the force field. Okay. So there is a tutorial in the website. This is the website for our group, the tutorial part, and you can search for FFTK. There are actually two tutorials. A tutorial about specifically the tool, force field toolkit, and then there is a second tutorial about generalizing the idea of parameterizing a novel residue. So kind of like they both touch up the same things, but the first one uses FFTK. So that's the one that we want to use. Okay, so let's open this. Okay, and right, and let's start from scratch. I think I have the files. Let me check. Yes, there is a question. Ramesh is asking, can we make a movie using text mode? Yes. So once you identify let's say you already identify what everything that you want in a VMD, the representations that you want, the position of the camera, the viewing angle, everything. Then you can save everything using those viewpoints, and basically use Viewpoint Render and Movie Maker in text mode, which is for once is faster because basically VMD is not loading, it's not showing you everything. And you can do that. Sometimes people use HPC centers like supercomputers to do these renders. So yes, that's a good point. In order to use the text mode, you need to know a little bit more about the scripting in VMD, which is, I think, I recommend, because that opens up a lot of options for you to do, not only regarding to movies, but also analysis. Basically, if there are a ton of analysis options in VMD, but there's always room for more, so you can create your own analysis using the scripting language, and you can combine different type of analysis. For example, you can run an alignment and then a contact map and different things. Okay. Sorry, I was looking. Let me download the files just one more time. The files. Let me open. Where was I? I think I was here. Yeah. So let me go to tutorial. Yeah, I think I have the tutorial files. Let's put this here. Okay, so we have here the tutorial. So the first thing that every tutorial comes with the introduction about the topic that you are trying to cover, which is similar to the introduction that I gave you. Like, for example, here is the same question, the same equation, where it tells you about the parameters that you need to find, and some things pertaining the general force field, the Champ general force field. Okay, so I think I can skip this. This is, again, the workflow that I mentioned earlier today. And okay, so the first section, the second section for this tutorial is called system preparation. And what it's asking you to do is to build a small molecule using Biophysics, which is something that I show you briefly in one of the animations. So let's do that, okay? And let me show you how to do that for a different molecule. This is so let's do extensions, modeling, Biophysics. And this is gonna open here Biophysics. Where is my display? Here. Okay. Let me change the color, maybe it's easier. Okay. All right. All right, so let's create. So let's create first the ethanol molecule, which is the main point of the tutorial. So it says, okay, go to build new molecule from fragment, which is, in this case, this is a update, is the new version that has the same features. So let's add independent fragment, and let's use methane. Okay, so now we have methane. And let's use, and then let's, so what we need to do now is to add another carbon. So we can do that by replacing this carbon here and go clicking there and go replace atom with fragment and do another methyl. Okay, so now we have a ethane. So the next thing is gonna be replace one of these hydrogens with a OH group. Okay, so we can do that. Let's replace this one here, the last one. So we click there and go to build, replace atom with fragment, and we choose hydroxyl. Okay. Okay, so now we have our ethanol molecule. Okay. And what we need to do now, if you remember, we want to generate the force field parameters for this molecule. So we need to use FFTK. And FFTK basically requires a system file, and a PSF file, and a PDB. Okay. So this is what I'm saying. I was saying that the interface of Molefacture changes a little bit, but the ideas are the same. So this question came up earlier about if you can change the atom names and atom types of these species, and you can. And actually, this tutorial suggests you to do that so that it matches the atom types of the general force field, the general force field. So we can follow this tutorial, and once we do that, we can export this PSF and PDB. Okay, so we click here and we select, let me change where am I? Tutorial files. And therefore this is gonna be ethanol. Okay, and I'm gonna save the PSF and the PDB. All right. Okay. So once we say that, we can go and start the following part of the tutorial, which doesn't need Molefacture anymore because we already prepared our molecule. And it's this part. Okay. So let's do that. Let's go in order, and then I'm gonna show you another thing you can do. Okay. So let's close Molefacture. And now it says start force field toolkit, GUI in modeling, force field toolkit. Okay. So the first part is creating an initial parameter file. So for that, I'm gonna use the files that are already prepared for this, the tutorial. So the PSF and the PDB are already there. So let's do that. It says navigate to the first tab, the build part tab, and expand this identify missing parameters here. So let's do that, and then populate the entries of the PSF and the PDB. Those are the files that you just created. So let's do that, and let's go to the files that are given by this the tutorial, the PSF here, and the PDB here. Okay. So once we load these files, we can go and click Analyze. And it's gonna give us from this PSF and PDB. Remember, this PSF and the PSF file contains all the bonded terms, basically all the bonds, angles, and dihedrals in my system And from that, it's gonna say, okay, there is a bond between an atom type CG331 and an atom type HgA3. These are the atom types that the tutorial suggested us to load. Okay, these are the properties that you can do. Okay, so that's great. And now we created a parameter file. We save this parameter file. We do that as save as par 0. Okay, let's do another one. A new par ethanol 0. And then we write the initial parameter file. Okay. Up until this point, we haven't done any parameterizing. We just identified the parameters that are necessary for this molecule. And we're gonna, the next step is gonna be to assign some of the missing parameters by analogy, okay? This is the second part. So let's close this or minimize this part. And now we have the second part. Okay. Okay, so now we are going to look at the parameters. So we're going to load the parameter file that I just created and load it. And it's going to give me a list of these non-bounded terms, the van der Waals or Lennard-Jones. If you remember, I said these are the parameters that are not being refined by FFTK. Those are parameters that are obtained by analogy. So let's do that. Let's obtain these parameters by analogy based on the atom type. So in order to do that, he says that we need to load these files, the topology and parameter file of the CGNFF server, of the CGNFF of the general force field. So do that. Let's do that. Let's click here and load topology and parameter file. And this should be in common here. So let's do the topology and the parameters. And these parameters are kind of like the whole force field, right? And we have all the atoms, all the possible atoms. So we need to filter. Let's filter by element and find the parameters, the van der Waals parameters, which are epsilon and r mine, for this type of carbon, which is the atom type is CG321. So let's browse this, and we can find here the CG321. And it says here that the comment is that this is an aliphatic carbon for CH2, present in alkane and other things. This is kind of comments from the file. Can you see that? Maybe the resolution is not very good, but so if you follow this, you can assign. Okay, so I do set from reference here, and I assign all these van der Waals parameters to the atoms that are in my molecule. Okay. Once you finish with this, then you're already finished with the van der Waals Lennard-Jones parameters. You can update the file here, clicking here, and it's gonna copy these parameters to the file. Okay. So let's skip ahead and so the next step in the tutorial is to generate some files for the calculation of the geometry optimization of the molecule. Because since I created this molecule using since I created this molecule, or you will create your molecule using a tool that gives you coordinates, but those are approximated coordinates. So you want to optimize. The first step is to optimize the structure using a quantum mechanical calculation. Okay. So the way you do that is to follow the interface, loading the PDB and writing down what you want, the name of the file that you want. You can select whether you want Gaussian or Orca. And then you write here the QM software input file. So let's skip ahead. And these are the instructions for the example of Gaussian, but it can be done in Orca as well. Okay. So let me show you let's use the results provided by the tutorial of this. So let's browse. This is the original PDB. The output file is here in this folder in example files 2, geometry optimization. This is the optimization log. And let's load this. What's happening? Let's try. Let's try with the Orca files. I have them here. Let me go to my website. So in my website, I have files for the tutorial if you were using Orca. Okay, so let me use those files. And let's see where I have them. Okay. So, unzip these files. Fine. So let's use these files they have here. I have the colors. I changed the colors, and I need to put this back. And of course, the background is making this a little bit difficult. Okay. So now I have these. So this is basically the results from the geometry optimization. If you look, let's make a nicer representation. Okay, so this was the original geometry, and when I run the geometry optimization, it converges to a different more. Okay, so it changes the bond length, especially, and the angles. Okay, so I get the new the new geometry. So that way I can generate a new PDB and continue with this with the steps to optimize the charge. Okay. Any questions so far? Sorry, I was going a little bit faster. Let's see. Okay, Mohammed is answering a question about scripting. Are you following along the tutorial? Do you have any issues? I'm not looking at the Slack right now, but hopefully the other TAs are. No? No questions? All right. So let's do this part, the water interaction part, together, okay? So for the charge optimization, we need to generate a series of files that basically probe each atom of the molecule by connecting or positioning a water molecule in different orientations to interact with that atom. And basically what we are trying to find is to optimize this position, this interaction, so that then we can mimic this interaction by means of playing around with the charge of the atom that gives the best results compared to the quantum mechanical calculation. So let's do that. Let's continue by getting the files. This is the PSF. And the PDB is the optimized PDB that we just did in the previous step. Now it's asking for a directory to create the files. And once it comes here, FFTK automatically characterizes the water interaction size in whether the atoms are donors, so they interact with the oxygen of water, or they are acceptors and interact with the hydrogen. So if we click here and auto detect, it's gonna tell us that atoms 1, 2, 3, 5, 6, 8 interact with oxygen. Those are mainly the hydrogens, okay? And atom 7, which is the oxygen, is going to interact with the hydrogen of the water. So when we create this, we select the software and create here, click write QM software input files. It's going to create a series of files, in this case, a total of 6 here and 1 here, and also an additional files that are necessary for the next step, okay? So we can see here that the example of all the water positions in the tutorial, and we can load these files by going to this directory and see these are all the files that were generated. Okay, so for example, this is a molecule ethanol. I created one acceptor water interaction pair with oxygen, which is this. So if we load this, we can see that this water is positioned in a way to interact with the oxygen here. And once we optimize this, So I have already did the calculation, and here's the optimization of that part. So let me hide this. So this is the initial position. I only want the last one here. Let me change the representations to CPK. I like this better. So now we can see that the initial structure was like this. The orientation of the water was that, so that the interaction between the oxygen in my molecule and the hydrogen of the water was simplified. So now I can see the geometry optimization basically identifies the optimal distance between these two species and the optimal orientation of the water, okay? So this is the result of the simulation. This is what I'm gonna use to estimate the charge of the oxygen here in my molecule, okay? So if I see all the results, okay, so I already created the files, and let's say I run the files, I have the results. So the next step, let's continue here, is gonna be optimizing the partial atomic charges of all these atoms, okay? And the way it's done is following this interface. You need to select again the PSF and the optimized PDB. And you need to add the parameter file that we were using. So that parameter file is, I think it's here. It is. And this part of the GUI gives you the option to use some constraints in the charges that you're gonna calculate. Okay, so if you have some chemical intuition about the charges, okay, oxygen, for example, has to have a negative charge. It can be a positive charge. So you can constrain the charge of oxygen so that it optimizes to a number that has some chemical sense. Okay, so the way this can be done is if you click here in guess, it's gonna look at the parameter file here, and it's gonna identify all the charges that could be optimized given this. And you may be interested in optimizing some of them, and other you may think they are okay. For example, in this tutorial, it suggests you delete the hydrogens, the hydrogens connected to carbon from here, because usually those hydrogens have an established charge, so it's pretty good, the charge. So you don't need to re-optimize that. So you can delete that from the list and only re-optimize the other atoms that are more important. Okay, they are like more. Those that could be changed. And here you have the example of the charge constraint. You see here that, for example, for oxygen, you are constraining the optimization to be between -1 and 0. So any negative number is fine, but if it goes to a positive number, I don't want that result. So let's not waste any time in the optimization going for a positive charge. And this is the initial charge that you get given the atom type. And this is the one that you may want to refine. So the way you do this is here you set up the net charge of your molecule, and then you recalculate the optimized sum of all these atoms. And then once you have this, This is a charge constraint part, so let's minimize that. You need to use here in this part, target data, QM target data, you need to show the plugin where all these results files, all these optimizations for the water interaction are located. So it's gonna ask you for several files that you already computed. And once you load these files here, so let's do that to see if you, how long it takes. So now it's asking me for the ethanol single point at Hartree-Fock level that is produced this MP2, the water, and then all these files that are here. So if we go to run optimization, in this case, it went fast because it's a small molecule, and I have the results here in this window. So this is then the final results, which are, did I use the wrong parameter file? Maybe, no. So these are the results for the charges, okay? So once I get the results from the charges, I can use those results to run a second optimization, because sometimes these results are need to be converged. So maybe you run once, you get the result for your optimization, you run again, you get slightly different results, an improved result, and so on and so forth. Because as any optimization, it depends on your starting point. So the closer, the more steps you do, and the more refinements you do, the best it is to make sure you're getting a good result. So once you get the good results, you can update these charges in a new PSF file by selecting your new PSF file and write that new PSF file with the new charges, okay? There might be sometimes, since this is an optimization, there might be some conversion issues, and that is why we have these advanced settings to change the optimization mode. You can change the tolerance, different other parameters for the optimization, but in principle, those are only necessary when you have issues with your optimization, okay? Optimization charges. Okay, let me stop here and see if there are any questions.
I have one question.
Yes.
With what method we choose the charge for new molecule? Are we using, do we use the quantum mechanical to quantum calculation to extract the charges, or how we get the charge?
The charges are extracted by first you set up, you get quantum mechanical calculations of basically what you're trying to simulate is this interaction between water and your molecule, okay? So once you have those results, the plugin, what it does is it uses those results to optimize the partial charge of your molecule that best resemble those results of the quantum mechanics, okay? Because that partial charge is what you're gonna use in your classical molecular dynamics, okay? You're not gonna do quantum mechanics of this system anymore. You just use this interaction between water and your molecule so that it mimics the interaction in the classical molecular dynamics, okay? So that's the idea. And the method that you use, the quantum mechanical method that you use for this is this method called Hartree-Fock. which is one of the cheapest methods, the simplest one. So this is the if you're familiar with quantum mechanics, this is the information that you provide to the software. Okay.
Okay, so why we do not use just a simple NBO or something like that in quantum mechanical to get the charge more accurately?
Oh, okay. The reason is that you're not interested for the charges of the molecule in vacuum, because the quantum mechanical calculation is simulating your molecule in vacuum, right? Or sometimes you can give some implicit solvent. You can do some implicit solvent simulations, but basically we are interested in the charges in the presence of water, okay? So if you do that and use MBO or other analysis to get partial charges, you could get some results, but those are not the ones that are used in the charm force field. The charm force field requires you to do this process so that it matches all the other partial charges. Basically, all the other partial charges that are in the force field, for example, the proteins, the lipids, nucleic acids, all of those have been calculated using this protocol. So if you want to add a new molecule, it's better if you use the same protocol to get the charges, okay?
Okay, so if I understand correctly, we just use quantum mechanical to optimize the structure just for optimizing the structure, and for the charges, we use the script, the software to guess the charge.
But also this plugin requires, So this plugin requires a series of calculations in quantum mechanics. First, the geometry optimization, and then this calculation that is the molecule with the water, okay? This is a quantum mechanical calculation as well.
Oh, okay. Now it's clear.
But the plugin gives you the protocol so that it generates all the calculations that you need. Then you go run these calculations and come back with the results and do this optimization.
Okay, thank you. Perfect.
Okay, and let me give you one more thing about this. Another thing that I wanted to mention for this. Let me remove everything. Okay. Sometimes you don't want to. So this protocol for FFTK, it's a good protocol to follow when you don't know anything about your molecule. You want to start from scratch, like create your molecule, everything. But let's say I want to use some information from the charm general force field. So the way you do that is there is this ZGNFF web server. Here is this website called cgnff.umaryland.edu. And so you need to create an account, but it's free. So the account is only for to avoid any DOS attacks, but basically just to keep track of people that use it. But you need to create an account, and then what you can do is you can click here and upload molecule once you create your account. And the way it works is you can use a PDB or a mol2 file for your molecule and load this into general force field and into this web server. And the same way Delara was mentioning that he used some web server to get parameters, you can also get parameters from this, okay? And as I said, these are basically given by analogy. So it looks through the database and it finds molecules that are similar, and it gives you those parameters from those similar molecules, okay? So let's do another exercise that uses this. So let's go back to Molefacture, and let's create a different molecule, okay? So I want to create the acetaminophen. If I remember correctly, there was a butane, sorry, a benzene. Let me just try to remember what was there. Okay, so there was a benzene on one side. Let's Google acetaminophen so you guys can see. This is the structure, okay? So let's replace this, this hydrogen with a hydroxyl. Sorry, replace hydroxyl here. On the other side, then we have this nitrogen. So let's replace this hydrogen with the let's do. So let's create a carbon first. We can do terbutyl now. Let's do methyl, okay? So now let's change this to nitrogen, okay? And we need to get rid of this hydrogen, okay? And now we can replace, the structure doesn't matter because we're gonna optimize this, okay? So even if it looks funny at the end, we are gonna re-optimize this structure. So let's change here. So I'm kind of like opposite to what this is showing here, okay? This looks like a little bit like this. So now we have here another carbon. So we can do, let's see what happens if I do carbonyl. Okay, great. So now I have a carbon and a double bond oxygen here. So now I need to add hydrogens. So let's do use this button to add hydrogens here. And he added one hydrogen. And let's now switch this hydrogen for a methyl group. Okay, that's it. So this is a very flimsy acetaminophen. Okay, let's check the bond orders a little bit because that's important. So you can see here that we have single bonds here. Here we have a double bond. Every other bond here in the ring, which is fine. Now we have here 3 bonds. That's fine for the angles and the hedrals doesn't really matter. Here we have a double bond. That's good, and this is okay. So now we have a structure for this molecule that is not very good, but at least all the parts and all the connections are there, okay? So what we're gonna do with Molefacture is we're gonna extract this using this mol2 file, okay? So we're gonna write a mol2 file. Let me go back to here. We have an acetaminophen. So let's call it a ACE mol2. All right. So now we can use this file in the web server. So let me scan. Let me go back to my home tutorial. Here I have my file. And so if we click upload, so it's gonna give us this the output here is this str file, which we can open. And well, let's see what we have here. Can you guys see the file? So this is actually it's a string file that the web server gave us that has both the topology and the parameters in a single file. Okay. Remember when I was explaining the topology of in the talk earlier today? So this is the residue is called ven because I started with benzene. That's why I kept the name, but I can change that. And now it's saying like, okay, each of these atoms that I created, it gave me the atom type that most resembles that, okay? And it gave me actually the parameter, which is the charge, the partial charge for that thing, okay? And in this case, in every time I get this charge penalty, which is something that the web server give us in order to tell us, okay, you can trust this parameter, or this molecule does not look like anything that I have in my database. Therefore, this parameter is very suspicious. You shouldn't trust that. And you should go and refine it with a different method, okay? But in this case, when the charge penalty or the parameter penalty is close to 0, we can say, okay, this is, or close to 0 or lower than 50 units. That's an arbitrary number, but we can say we can trust that number, okay? So in this case, I created acetaminophen, and probably because this molecule was already in the database, I got the partial charges and the penalties are 0. So I can trust this value, okay? Let's see what else is here. Okay, so it didn't give me any bond angle and dihedrals parameters. Okay, so let me go back here and let's upload it again. But this time I'm gonna select the same file. But this time I want to click here in include parameters that are already in CGNFF, just so that we can see them, okay? That doesn't mean it's necessary, but okay. So let's upload this again. And now we have a new str file that now has, so this is a topology part here. And now we have the parameter file that I show you, where we have, for each bond, we have a line that defines that bond between these two atom types. Okay, let me make it a little bit bigger. And the reason why it didn't show first is because these are already defined in the force field, in the files that come with the force field. So basically, it tells you that you really don't need to specify them again, because as long as you use these atom types for your molecule, the bonds that are given here are already covered in the force field, okay? But nevertheless, I want them to show because I want to discuss them with you, okay? So these are the values that are corresponding to each bond, each angle, and each dihedral, okay? And since these parameters were already in the force field, there are no penalties for these parameters. But if you were to get parameters that were not in the force field, you will get an associated penalty parameter that you may choose to refine or not, depending on the value of that penalty, okay? So, and then what you can do is use FFTK to analyze this str file. So let's close Molefacture because that's already, oh wait, I need to create a PSF and PDB. And now I can close it. And let's open FFTK. And we are almost at the time. So now I want to use this third part here, prepare parameterization from CGNFF program output. So if I click here, it opens up this, this part where if I input the Mol2 file that I created and the CGNFF str file here. So sorry, I didn't save it. So let's save it. So we can save it by, I think the way I do it is basically just copy everything and open the BI, dump it here. Okay. So I save this file and I'm gonna scroll towards this file, it's downloads here. Okay, so it asks us to select a folder. Let's select this folder. And so we can analyze the input. Okay, so, and again, it doesn't show any parameters here because everything is already in the force field, but it's gonna show everything that is missing, that is not in the force field. And then we can write this new parameter file with those parameters that are missing and use FFTK to refine those parameters, okay? So that's another way to start your problem. Instead of starting from scratch, using the first part, which is this one, identify missing parameters, you can go create a Mol2 file, use the web server, the CGNFF web server to get a string file that has the topology and the parameters, and then come here and analyze that file and get basically the list of parameters that you need to evaluate, okay, and refine. Are there any questions? Okay, if not, you have time for the rest of the afternoon or evening or wherever you are in the world. We have 1.5 hours more of today to play around with this. You can play around with the FFTK. If you are still working through the free energy, you can do that. And we can answer any questions that you have. Hopefully through Slack. And as a reminder, these sessions are being recorded, so hopefully the recording is gonna be available by the end of the week because it needs to be post-processed and edited and other things. So if you missed something, don't worry, you will have time to go back at your own pace with these recordings after the workshop, okay? Okay, I'm gonna stop sharing and let's take 15 minutes break. And then we can answer any of your questions.
Excuse me.
Yes.
Oh, sorry. I have a question about the recorded videos. Are you going to share them on YouTube as some other previous workshops, or you are going to send it to the participants?
Yes, it's going to be available to everyone through YouTube.
Thanks a lot. That's great.